First of all, I'm very sorry that this video is going to be a bit longer than my previous ones because I don't want my viewers to miss each and every little details about a circuit. Today I'm going to demonstrate the Astable operations where I'm going to discuss the circuit analysis, design steps on LTspice and the functionality of the circuit using some animations so that you can understand the functionality of the circuit with a very greater details. Now, Astable. Why it is called Astable? Because in my last tutorial where I have demonstrated the monostable operations, you have seen that it had only one stable state, and that was the ground state. And it jumps to the quasi-stable state. And here you are gonna see that the output is not going to stick a particular states. Rather, it's going to oscillate or toggles between the positive supply and the negative supply. The negative supply is obviously the ground or zero voltage. So that's why it has no stable state and it's called the Astable operations. So basically, an Astable operation means the waveform looks like a square wave. Although you can generate a square wave using an operational amplifier with a capacitor resistive network at the negative feedback terminal and a resistive network feedback at the positive terminal of the operational amplifier. But the major difference while using an operational amplifier and using a triple wave timer IC is that when you are using the triple wave timer IC, you can modify the on time and off time within a particular period, which is not possible when you are using simple operational amplifier and a capacitor resistive networks. So that's the thing I'm going to use over here, and exploiting that particular property of Astable operation using triple wave timer IC, you can design a pulse width modulator or a voltage control oscillator. So these things also I'm going to discuss in this tutorial too. If you find this video is helpful for you, then please like, share and subscribe, and please comment on various topics. If you want me to make videos on your choices, please stay tuned and bother me a little bit for this particular video. Here I have presented the monostable circuit and the Astable circuit side by side in order to have a good comparison between them. You can go to my previous tutorial regarding the monostable operation. The link is given in the description box, as well as you can go to my playlist of analog circuit where the entire lectures on monostable and Astable operations are given. And basically these two slides I have taken from those two lectures. So the same slide I'm referring for better understanding. So as you can see, in the case of monostable operation, the discharge pin and the threshold pin, they were shorted and they were connected across the capacitor. On the other hand, the trigger terminal is open to take the trigger signal from any sensor, as I have explained in my last tutorial also, that if you have a smoke detector or any anti-theft alarm detector, which is usually a motion detector, so you can connect it over here, so that will trigger up this device, and the output will stay at its quasi-stable state during the time the capacitor is charging from 0 to 2/3 of the VCC. When you look at the Astable operation, you just observe the connection. The discharge pin is right now is connected between these two resistors R1 and R2. On the other hand, the threshold pin and the trigger pin right now, they are shorted and gets connected across the capacitor. Unusual operations remain same. That means they are comparator, they are RS flip-flop. So they are all working as they are working for the monostable operations. But the only difference is that the trigger right now is connected with the capacitor. So basically, in case of monostable operation, you need to apply a trigger from the external sensor or source. So here you do not need that thing. So when the capacitor voltage will rise up, so automatically the trigger will be applied. So when the capacitor voltage will rise up, initially the operation almost equal to the monostable operation. That means at the beginning, when you have applied this VCC, So that VCC gets divided as the 2/3 of the VCC at this node and 1/3 of the VCC at this particular node. And this is the non-inverting node of the lower comparator or comparator 2, and but this one is the inverting node. So when this trigger terminal is connected across the capacitor and the capacitor is not holding any charge initially, so the potential at the inverting terminal of the comparator 2 is 0, which means the potential at the non-inverting terminal is higher. That will make the output of the comparator 2 to be saturated at plus Vset. So that will be the corresponding input for the S as logic 1. On the other hand, if you look at the input for the comparator 2, so here the pin number 5 is grounded through the capacitor, as usually I did for the monostable operation also. In this case also I'm doing the same thing. This terminal, the control voltage, is grounded, but the threshold voltage, pin number 6, is also shorted with the trigger voltage, and it is also connected across this capacitor. So basically whatever the trigger voltage is getting, the same potential is appearing for the threshold voltage pin number 6. So at pin number 6, which is the non-inverting terminal, that is 0, but the inverting terminal, there 2/3 of the VCC is appearing. As a result, the output of the comparator 1 is switching to minus Vset, and that is corresponding to logic 0 input to this R. So right now, logic 1 to this S and logic 0 to the R, and that is corresponding to the set state. Set state means Q will be 1 and Q bar will be 0. When Q bar will 0, output will switch to the plus VCC. And when Q bar is 0, this transistor is turned off, and this path right now doesn't exist. So the current will flow through the resistor R1, since this path is disconnected, or a high impedance path I can say. So the current will find the path through this R2, and here the threshold and this trigger, these two terminals are the input terminals of the operational amplifier. So we generally consider that they are, the input impedances for the operational amplifier are so high that literally very negligible current can flow through these pin number 6 and pin number 2. That's why the majority of the current should flow from the VCC to this R1 and to this R2 through the capacitor C. And during the time, the capacitor will charge up. Now, when the capacitor is charging up from the 0 voltage and it's reaching to 1/3 of the VCC, so what is happening over? Look at this comparator 2. When it just crosses the 1/3 of the VCC, which is the reference voltage of the comparator 2, then the output of the comparator 2 is switching to minus Vset. On the other hand, the output of the comparator 1 is not switching right now, because potential at its non-inverting terminal is still less than that of the inverting terminal. So therefore, it remains at minus Vset. So that means the 0-0 condition is appearing for the R and S input. As a result, no change will take place. So that means the transistor remain turned off, the output remains at the plus VCC, and the capacitor is keep charging up. Now, during this charging, when the capacitor voltage reaches the 2/3 of the VCC, this is the condition as you have seen in this case. When 2/3 of the VCC, the capacitor voltage reaches the 2/3 of the VCC, then this upper comparator or the comparator 1 switches its value. So here also the threshold pin number 6 right now is going to get a higher value compared to its pin number 5, which is the inverting terminal. As a result, the output of the comparator 1 is switching to the plus Vset, and that means the R input is logic 1, whereas S input already is maintaining at logic 0. So 1-0 for R and S, that is the condition for reset. So the flip-flop will go for the reset. Reset means Q will be 0 and Q bar will be 1. Q bar will be 1 means output will switch back to 0 state, and this transistor will turn on. And when this transistor will turn on, there will be a short circuit or there will be a lowest resistive path that will be established between this pin number 7 to this ground. As a result, the capacitor will start to discharge through this pin number 7. But the only difference between these monostable and these astable is that in the case of monostable, the capacitor discharged instantly, because as you can see, the capacitor is connected between the pin number 6 and pin number 7. They're shorted. So this is the pin number 7. So when the capacitor value reaches the 2/3 of the VCC, this transistor turned on and there exists no resistance between the capacitor and between this path, between the ground within this path. So that's why the capacitor gets discharged instantly. But there's a difference in this astable case, because in between this node, there is a capacitor and the discharge node, there exists a resistor R2. So that's why the capacitor will take some time to be discharged from the 2/3 VCC to 1/3 VCC, because when the capacitor is discharging and it is taking some time, and that time depends upon the time constant R2 times C. So taking that time, when the capacitor is discharging and it's discharging back to 1/3 of the VCC and just became slightly less than of the 1/3 of the VCC, then you can see the potential at the non-inverting terminal of the comparator 2 will become higher than its inverting terminal again. As a result, the output of the comparator 2 will switch to the plus VSAT. On the other hand, when the capacitor was discharging starting from 2/3 VCC and it's just reduced down below the 2/3 of the VCC, automatically the potential at the non-inverting terminal, the potential at the inverting terminal of the comparator 1 already got higher than that of the non-inverting terminal, resulting in the output of the upper comparator to switch at the minus VSAT. So right now the condition is the lower comparator output is plus VSAT and the upper comparator output is minus VSAT, and that is when the capacitor is discharged to the 1/3 of the VCC. And this is the condition for the RS flip-flop is S equals to logic 1 and R equals to logic 0, and that means the flip-flop is going to set state again, and the Q bar is going to logic 0. So logic 0 means the transistor will be turned off, the output will switch to plus VCC, again the capacitor will start to charge up. So in this way, a charging and discharging of the capacitor will take place, and as a result the output will switch between the plus VCC to ground, plus VCC to ground. And as you can see, the output you can have the square wave. So basically astable multivibrator or astable operation we call, because unlike the monostable where we had only one stable state, that was the ground state, and when you have applied the trigger, the output switches to its quasi-stable state. But here, as you have seen and you will see next through some animations as well as in LTspice, no stable state exists for this particular operation because the output switches between the plus VCC and the 0. So that's why the toggling output is expressing that there is no stable state. So that's why it's called astable operation. Now I'm going to explain you the astable operation using that animation. Well, so this is the circuit I have designed to demonstrate the astable operations using some animations. And here this 2 kilo ohm resistor that is being used as the R1 and this one as R2 if you compare with the presentation that I have shown just before. And this is the capacitor that will contribute in charging. But just look at this charging and discharging time through the resistor R1 and R2. You will see that during the charging time of the capacitor, which means when the capacitor is charging from the 1/3 to 2/3 VCC, in that case the charging time is more compared to the discharging time, because during the charging time the capacitor, the current is flowing through both this R1 and R2 resistor, and that's why the charging time is greater, because during the discharging time the capacitor is using only this resistor R2. You may think that you can make this discharging time greater by replacing this value of this R2, say for 4 kilo ohm, but no, you can't, because in that case the charging time will be 2 plus 6k, so 8k will be contributed within the discharging time, whereas the 4k will come 6k. If you consider this one is 6k, if you replace 1k as 6k, so the charging time will be depending on these 8 kilo ohm resistance, because these 2k and 6k, this 2k and 6k, that will make this 8k, whereas the discharging time will be based on the only 6 kilo ohm resistance. So always you cannot make the on time, means when the output will stay on, so that will be longer than the time when the output will stay at the zero state, and that is because of this charging and discharging time. So let's see how it will happen. And one more thing, here I have connected two LEDs. As you will see, this LED is connected directly to this output, so when the output will be on state, this LED will glow, and when the output will be in off state, this LED will glow. So as I have explained that the on state is longer than the off state, so this LED is going to glow a longer time compared to this LED. So let's start the animation, how we can see. As you can see this one, so this is the on time, this is the off time. Now if I see the voltage across the capacitor, look at here, capacitor is charging, discharging. So during the charging time of the capacitor, the output remains high, and during the discharging time it remains low, but the charging time is longer compared to the discharging time, as I have explained. You cannot make this equal by this orientation. Yes, but you can make them equal. So I will show you next how we can make the on time and off time equal to each other, and it can be done easily using this particular configuration here. As you can see, now I have used these two resistors equal to each other, and here I have placed two diodes. One diode is confirming that this current will flow through the 2 kilo ohm resistor, then this diode, and then it will charge up the capacitor. So during the charging of the capacitor, only one resistor is contributing. On the other hand, this diode ensures that no current should flow through this resistor during the charging up. And during the discharging operation, the capacitor, when it will discharge, the current will flow through the diode and through the resistor and through this discharge pin, because at that moment, when the capacitor will reach the 2/3 of the VCC, this discharge pin will be shorted with the ground, and it will find the lowest resistive path through the discharge pin. So that's why it will discharge through this one. And this diode, at that moment, it will ensure that the no current from the capacitor will pass through this direction. And now if I run the simulation, so you can see this is the transient state, this is the transition, so just ignore this state. Now when the output will be stabilized, as you can see that it's appearing with perfectly equal on time and off time. And this is I have achieved using these two diodes. And here I can control these on time and off time much better way than the previous case, as I have explained when there was no diode. Because right now this R1 resistance and the R2 resistance, they are working independently. So if I want to make this on time shorter than the off time, then I just need to replace this 2 kilo ohm resistance with the smaller value. And if I do this, so look at here, the on time became smaller compared to the off time. In a similar manner, right now if I want to make the off time is shorter than the on time, then just I need to replace, or I need to just increase this value. If I increase this value, then on time will be longer and off time will be comparatively shorter. So right now I have gained better control on this on time and off time, which was not possible in absence of these two diodes. Now another interesting thing I'm going to explain it over here. So that is associated with these control pin that I have told you in my previous tutorial that I can do many interesting things using this control pin. So that's the thing I'm going to explain right now. Well, here what I did, I just replaced the capacitor by a sinusoidal source of 1 kilohertz because the output switching was very high frequency, and compared to that I have used a very slowly varying signal at the control voltage. So what I'm going to gain, if you see the internal circuit diagram, at that point I must show you the internal circuit diagram once again. So this is the internal circuit diagram where you can see the pin number 5 is the control voltage, and here I have applied a sinusoidal voltage source having frequency much lower than the output switching. So therefore, as you can see, the potential at this point is going to change much slowly than the capacitor is charging and discharging, or the output is switching from the plus VCC to ground and vice versa. So as a result, as the threshold voltage is going to change, the width that is being controlled by the threshold voltage, because the capacitor that needs to charge more than the threshold voltage in order to alter the output, so that is right now varying. So as this is varying, so when this potential is rising than this 2/3 of the VCC or something else, so the capacitor will charge up to that point, and that's why the capacitor charging and discharging of the capacitor must be in a higher rate compared to the rate at which the potential at this point is changing, because the capacitor must have the sufficient amount of time to cross that amount of voltage, that dynamic voltage that is changing around this particular node. And when the capacitor voltage is becoming greater than the dynamic voltage, at that moment the output width, the pulse width of the at the output, that also is changing. On the other hand, when the capacitor is discharging, during that time the potential at this point is also changed, because this is right now a sinusoidal signal I have applied, and that's why in the next time the capacitor needs to reach a different voltage than it has reached in the previous case. So that's why the pulse width gets modulated, and in this way you can get, or you can design, a pulse width modulator, as well as this can be treated as voltage control oscillator VCO. I will show you when I will demonstrate in the LTspice that as the pulse widths are changing with respect to the applied voltage, so that is the property of a voltage control oscillator, because the frequency gets changed with respect to the input voltage. So as the pulse width is changing, the frequency is also changing continuously. I will show you. Right now, I'm going to show you using this animation that how these outputs are changing with respect to the applied voltage. So this green color, it represents the applied voltage, the sinusoidal voltage of 1 kilohertz, and this purple color, that represents this one represents the output voltage that already I have shown you. So now if I run it, as you can see, if you ignore the transient state at the beginning, so when the input is changing in a negative direction, as you can see, the pulse widths are much more closer to each other. On the other hand, during the positive direction, they are coarser, and along the negative direction, they are much more denser. Because here in this animation, I didn't show you any calculations regarding how to choose this R1 and how to choose this R2 based on the capacitor and based on the requirement of your on time and off time. So that's the thing I'm going to explain you on the LTspice platform. So here the LTspice interface, I'm going for new schematic and going to search for the component of 355 timer. From here, I will skip the entire design steps for the Astable multivibrator. If you are not familiar with the LTspice, you can go to my tutorials, which are listed in the playlist of the LTspice tutorial. The links are given in the description box, and as well as you can click on the card that is appearing right now over here to see the LTspice tutorial. With this, I have completed the circuit configuration for the Astable operation. Now, I just need to put the value for this R1, R2 and this capacitor C2. So, how can I do that? Basically, here I need to do some calculations. So, for that, I should open Maxima. But before going to Maxima, I just need to write down the two equations that is applicable for the charging time and for the discharging time. So, generally, T is the total time period is equals to T on plus T off. So, this is the time during which the capacitor gets charged up to 2/3 of the VCC, and this is the time during which the capacitor discharges from 2/3 to 1/3 of the VCC. And the calculation shows that this calculation you can find in my lecture series on analog circuit, where I have explained in detail the calculation how you can get the exact expression of 0.69 times R1 plus R2 times C. And why R1 plus R2? Because during the charging time, two resistors were contributing over there. So that's why this one. And it approximately can be written as 0.7 R1 plus R2 times the capacitor. The entire calculations, everything is explained in my lecture series. The link is given in the description box. If you are interested to know the calculations, I request you to please go over there and just see how I have calculated these things. And for T off, this is 0.7. Basically, this also comes at 0.69. I am approximately writing this one as R2 times C. So this is the two equations, and these two equations forms this equation, this one. And here, F, the frequency with which your Astable multivibrator will oscillate, so that is F equals to 1 over T. But only knowing the values of T, you cannot design your Astable multivibrator properly, because as you have seen, the particular configuration that I have drawn without the two diodes, so there you must specify the on value and off value, and from there you need to design this R1, R2 and C, because out of these two equations you have to assume one thing, that is either C or R1 you have to consider. It's better to consider the C. I'm going to consider C as the 0.1 microfarad, the same value that I have considered for the monostable operation in my previous tutorial. I'm going to calculate the same thing. T on, I'm going to set for the demonstration purpose to say 8 millisecond, whereas T off is going to set 2 millisecond, having total time period of 10 millisecond. Okay, so how can I do that? So in Maxima, I'm going to put this expression with this value of the capacitor. This is the one equation, and in the second equation, I'm going to put this expression where with the T off of 2 millisecond and the capacitor value is this. And from these two equations, I'm going to solve the two simultaneous equation, although you can do it yourself manually. But in Arista, along with electronics and optics, you're gonna learn about many open source and the free softwares which are equally powerful as their commercial counterparts are. And experts all over the world are also recommending this software, because I can understand, being a student or a ground level researcher, you need support of these commercial softwares which involves a lots of costing and funding. And that's why as an individual, I do support to use these open source and the free software which are equally powerful to those commercial softwares. And that's why I have chosen the LTspice, because lots of circuit simulation softwares are exist in the market, and LTspice is free and equally powerful to those ones. Next, I recommend you to use this Maxima, because Maxima is equally powerful and it's free to use in place of its commercial counterpart like Maple, like Mathematica, and many other one. And in my next tutorials, I will let you know many other such type of open source and free softwares that can help you for your research, for your academic purposes. Anyway, so here I'm going to use these two equation, and now I'm returning back to maxima. So equation, solve linear equation. So right now I have two linear equations. One is 0.7 times R1 plus R2 times 0.1 E minus 6 microfarad I have assumed, and this is the on time, and that is going to be the longer one, 8 E minus 3, 8 millisecond. And equation 2, that is 0.7 times R2 times 0.1 is equals to 2 e to the power minus 3, 2 millisecond. Well, and variables are R1 and R2. So these are the two values, and I need in numerical form. So this is the value for R1, and that is going to be 85 ohm, 85 approximately 85.7 ohm, and it's going to be 28.6 ohms. Okay, so R1 is 85.7 ohm I'm going to use. So 85.7 K, not ohms, 85.7 K kilo ohm, and here 28.6 K, 28.6 K for the value of the capacitor 0.1 U. Well, I hope everything is set. So now I can run my simulation. So here, before that, I need to place a simulation command, and that is, well, 10 millisecond is going to be our period. Okay, so I'm going to observe the 5 period of mine, and that will be, say, 60 millisecond will be enough for that. Well, so now this is the output. Look at here, the longer on time and shorter off time. And if I take the capacitor value, so this is a transient state, and if you ignore this transient state, it's discharging time. During the charging time, the output remains on, and this is a discharging time which is shorter due to this resistor. Only single resistor is using, so that's why shorter discharging time and resulting in the shorter off time that I have already explained. Now let's see, I have designed the on time should be of 8 milliseconds and off time should be of 2 milliseconds. So let's see whether it's being maintained or not. So right click, first and second, both of them I need. So here I'm going to set first one over there. This is the first one, and this is the second one. So the time duration horizontal, the time duration along the horizontal axis is going to be 13 millisecond. It's a bit much longer. Oh, sorry, I made a mistake. The entire thing I'm calculating a wrong way. So basically, I need to check the difference. I'm observing this one. I have to check the difference. So this is the difference. Difference along the horizontal axis is 7.9. Yes, it's matching. So I'm confused a bit. Anyway, so 7.94. If I zoom it in, and if I place it much precisely, so I may find it 7.939. Okay, so it's appearing close to our desired result, that is 8 millisecond I have assumed, and out of that 8 millisecond it's appearing 7.92. so result is good enough. And if I check the off time, it should come 1.952 millisecond, almost close to 2 milliseconds. So it's fair enough for our design. Now, as I have shown you in my animation that I can make this design for the 50% duty cycle, because the duty cycle means there are on duty cycle and there are also off duty cycle. The on duty cycle means the duration for which the output remains at the on state out of the total time period, and off duty cycle means the duration over which the output remains on the off state out of its total time period. So basically, on duty cycle means T on divided by total T, and off duty cycle means T off divided by total T. So 50% duty cycle means on time and off time, they will be equal to each other, and that I can make it using two diodes that I have explained already using that animation. Now I can make a little calculations, because every time the current is going to encounter only one resistor. So if I, right now if I want to make my total time period of 10 millisecond, so in that case, so it will be 0.7 time R times C is equals to 5 millisecond for one half. And for that, so right now if I put that 0.7 times R times 0.1 is equals to 5 millisecond with the variable R, because I'm going to design my Astable multiplier for the 50% duty cycle, so, and that will be 71.43 K. Now I'm going to run my simulation, and I'm going to check the output whether it's appearing close to 5 millisecond, 10 millisecond or not. So now let's see whether they are appearing according to our design or not. Look at here. Instead of having the 5 millisecond difference, I'm getting 5.9 milliseconds. So the 0.9 or a bit higher millisecond difference. That is almost 1 millisecond difference I'm getting, and that is due to the forward bias resistance of these two diodes. Okay, so there exists two forward bias resistance, so that has a little contribution. That's why we are getting a little millisecond greater than what we have designed for that. And if you want to design for 5 millisecond precisely, then you need to reduce these values of 71.4C, go for trial and error method, and you will get your value. Well, now let's see the most interesting thing that I have explained, that is the pulse width modulation, or the VCO, operation of VCO. So I'm going to get the voltage source, and but one problem is that I have designed for these periods for the 10 millisecond, and 10 millisecond means so 0.1 kilohertz, or that is 100 hertz. Okay, so that's the problem. So right now I need to change it, because as I told that this frequency will be much lower than the frequency with which the output is oscillating. But in this case, the output I have designed is of 100 hertz. So I think that is not going to work, or it should work, but it will not be visible in a clear way that I have shown you in the animation. So that's why I need to change these values. So if I need to change these values, so I need to change it. If I consider a 5 kilohertz signal, or say 10 kilohertz signal, so here I have assumed the time period will be a 5 millisecond. Now I'm going to increase my output switching time. So I'm going to set the output frequency will be of 10 kilohertz. So if it is 10 kilohertz, then the uh, total time period is going to be of 1e 10 to the minus 10 to the minus 4, and here I can set for the half period it should be minus 4 and it should be 0.5. So this will be for the half of the period for the frequency of 10 kilohertz. Okay, and for that the value should be 714 ohms, 714.3 ohms. So I'm going to replace 714.3 ohm and 714.3 ohms for the capacitor value of 0.1 microfarad. And now if I run, what is the problem? Okay, the problem is that here I didn't mention any values. Okay, so just a minute, before applying this voltage, I just remove this one and I put it back with the capacitor value, because I need to check whether it is coming properly or not. So this 1U. Now if I see the output, okay, so huge frequency, such a large frequency, so that's why they are not visible. Well, so they are coming very good, and if I check the on time and off time, I mean the difference between the on period, so 0.59 microsecond, almost it's coming. Okay, so it's fine, our circuit is working properly. Okay, now I'm confident enough to put the values or the voltage source, and this voltage source, as the frequency of the output is 10 kilohertz, now safely I can put a sinusoidal signal of frequency 1k. Now the amplitude, and one thing that you should be careful about, that the DC value you have to put at the center of the maximum rail values available in the circuit. So maximum rail values are the 8 volt and 0 volt. So the center value of them is the 4 volt. So that DC volt you should apply it, because this voltage is going to be applied at the pin number 5, the control voltage, which is going to be used as the reference voltage for the upper comparator, the comparator 1. And if you do not put the positive voltage and the amplitude, that the peak amplitude of the sinusoidal signal will be so that the when the amplitude will go to the negative direction, then from the DC voltage the peak value will be subtracted, and then the total value must not go below the zero value, because if it go to the zero value, your upper comparator is not going to work, because at that point of time the reference point is going to get the zero value, and the charging and discharging of the capacitor remains within the 2/3 and 1/3 of VCC. But if you put the sinusoidal voltage such a way that it should go less than the zero voltage, then the capacitor voltage cannot charge up to the VCC, and your output will not work properly. So I'm putting here the DC voltage of 4 volt and the peak voltage of 1 volt, so that the negative peak voltage will not reach the zero voltage. So now I'm clicking OK, and now let's see what will be our circuit. But for that I need to, okay, but let's see. This is the sinusoidal signal, but for that it's so wider window I have chosen. I'm going to choose say 100 millisecond to 110 millisecond. Well, I think it should work in a good way. And next, the output. But look at here. During the on time, if I zoom in any period, during the on time, I mean during the positive peak of the sinusoidal signal, the on time uh, becoming wider, and during the negative peak, the on time becoming shorter than that of the off time. Okay, so this is the pulse width modulation you can achieve using this stereo timer IC and with the Astable operation. Now, if you want to check the frequency of the pulses, output pulses coming out from the stereo timer, you will see during this on time, if I check it at this particular position, and the 2 at this position. So this is one period. So one on time, one off time. So that is corresponding to the difference is 123.26 microsecond. So this is the total period during the positive peak of the input sinusoidal signal. On the other hand, during the negative peak, if you want to check it, so from here, on time, look at here, only 91.517 microseconds. So the period is smaller. So that means the frequency gets modulated during this position. So this is the example that using trigger timer, you can design your voltage control oscillator also. Well, if you think that this video is helpful, please like, share and comment, and click the bell icon to get the notification regarding my next video, where I'm going to give you much more informations other than the technical ones. And please put comments on the different topics. If you want make me to video on those particular topics, I'll be happy to deliver my tutorials on your choices. Till then, thank you very much for being with me.